All right, welcome back. It's done. It's done. I got it working. I figured out it was actually a software glitch, so I'm happy that it works. But I'm done with this. My curiosity has been sated. I'm not gonna really develop this anymore. I think, yeah, I'm happy with it. So what I'm gonna do with this video, first I'd like to talk about. I found out this thing can actually measure DC voltage just fine. In fact, 1.5 volts is the lowest I can get this thing to turn on all by itself. I wish I had known that earlier, or I could have avoided blowing out the USB port to my computer, but whatever. There's a little power button on the back, and boop, 1.5 volts. So this is actually very handy because I can adjust this. I have a little voltage divider on the back here with this potentiometer. And this was very useful for debugging because I could set a voltage that I wanted. I knew exactly what it was displaying. I could make it display whatever I wanted, and then I could make sure it was reporting the correct values. So I got this working. So what I'm going to do, and I'll put some links in the doobly-doo thingamahoots. Source code for the Arduino. It's not much. It's far from complete, but I think you can get the general idea of how it works from that. I'll make sure to add some extra comments just to make sure it's clearer. And I'll take this apart piece by piece and kind of show you how it was put together a little bit more than just showing it to you. Plenty of electrical tape because that's what we do. There's some alligator clips to hold these on. So these are just going from the voltage divider here. Boink. So I can use this to just set a reference voltage. Put all that junk aside. Battery snap. I should probably disconnect this battery entirely, actually. The battery is the only thing that isn't glued on, because you might have to change the battery. And getting the glue off is actually not that difficult. It's actually easier than getting the freaking tape off my fingers. Come on, there we go. Yoink. And let's see if I can get this battery snap off in one piece. Oh, that was easy. Don't want to short out the battery either. I'm running low on 9-volt batteries. A little bit of tape here. Yeah, so this thing will reliably turn on down to 1.5 volts. And as you saw, it self-initiates. So you don't necessarily need to plug this into anything to get it to work. Just make sure that the negative terminal of the battery goes to the neutral side, which, if you're looking at it from this side, is this one here, which I clearly have it marked because I'm not making that mistake again. And yeah, you can put any voltage you want in there, hypothetically up to, this device is rated up to 115 volts, 15 amps, nominal. So, you can probably put, well, it's got a capacitive dropper in there. You can't power this off of the DC. Get that battery back. Right? Like if you just jam the battery onto the terminals like that, it's not going to turn on. Because the power supply in this is a capacitive dropper, and of course the capacitor completely blocks direct current. So you still have to power it using the wires, but you can apply any voltage you want here and basically use it like a voltmeter, I guess. Huh. That's interesting. You're definitely better off buying a decent, real, well, okay, a decent one. This is a half decent one. But yeah, you can use it as a voltmeter. Not a very good current meter. This will not measure reliably below about maybe 2 amps or so. And that's because of the shunt that they use in it, which maybe I'll show you in a bit. This purple wire here ties the grounds together. And that's what blew up the last Arduino. I have a wire here that goes from the 5-volt output here. I'm using the 5-volt regulator on the Arduino to power the comparators here, because all these require 5-volt logic, and I don't have a 5-volt lead coming out here. I'm only putting in roughly 9 volts off the battery and relying on the regulator inside the kilowatt to provide the internal circuitry with its 5 volts. So I had to patch that in. That can be done a little bit better. All of these here, and I'll release diagrams to show you, what pins go where. It's pretty straightforward. But these are all the data pins. Just yank all these off because I'm going to want them back anyway. What a mess. Yep. Just pluck them all out. Whatever. what's important that all of these are all the data, right? That go right in here, and there's 16 bits worth of data that this thing inputs. These 4 here are the rows, right? These are all the columns, but these are the rows. So you have 4 rows, and these are on these pins particularly, 18, 19, 20, and 21, because these can be configured as external interrupts. So the software actually monitors these and runs an interrupt routine. Whenever one of these triggers, it inputs the 16 bits from here, pretty much in one shot, and stores it in a global variable, and then basically enables the next interrupt in the sequence. So you go row, I ended up doing it based on my nomenclature, row 4, row 3, row 2, row 1. And after it's completed all that, it disables all the interrupts and then goes back and processes the 4 rows just using basically bit masks and shifts and whatnot. So we'll take those out. This is going to be a bit of a bear to get off. Usually, and it's only because there's a lot of pins here, and I don't want to break it. Come on, easy does it. But I also want to be careful because the last time I tried to just yank this out, those pins go straight into your thumb, and that's not fun. This is the little header I made a long time ago. It has served me well. A little diode here. This protects the battery from reverse voltage. When this thing is plugged in and powered, there's an internal power supply that generates about 14 volts or so. And that's regulated down to the 5 volts that the internal logic needs. But since I had the battery hooked up directly to that, I used this little diode just to prevent current from going back up into the battery. Just some jumpers here. Okay, and now we're just dealing with the hot melt glue. So I'm going to show you a little trick for this. And I don't know exactly how it works, but if you want to get hot glue off of plastic, what I found to work really well is rubbing alcohol. And again, I don't know how this works. I think what happens is that the rubbing alcohol is just a thin enough liquid, like oil might also work if you want to use oil, but I think the rubbing alcohol is much cleaner than that. And if you just get under it just a little bit, like you can see this is like, yeah, that was on there pretty good, right? And I'm not going to do that with your Arduino because I don't want to snap the board in half. This actually comes off pretty clean. This type of plastic doesn't really adhere very well. Now that's on there real good. Like I glued that on there. So what I've done, I got a little bit of rubbing alcohol in the syringe here because it's just very convenient to just dispense just a little bit. You only need a little bit. Oop. That's probably way more than I needed. That's fine. But now once the alcohol gets under the glue, it just comes right off. And it's certainly not dissolving the glue or anything. And it's definitely not dissolving the plastic either. It just helps the glue release, and it releases very clean. There's no like that's a defect in the plastic. That's not extra glue that's on there. Actually, I think I might have melted it a little bit with the hot glue gun. Oh well. But yeah, that'll a little speck in there too. And the alcohol will just evaporate and you'll be fine. Because you clean electronics with alcohol all the time, right? It's fine. So to get this off, again, little dab will do ya. I got 2 more bits over here. A little bit there. A little bit there. Give it a little wiggle. See, I'm getting it all over the place already. Doink. No effort at all. It's fantastic. It'll even come right off the board here. Doink. Is that a little residue? A little bit of residue? That's fine. Pulls it right off. I really don't know how it works, but I'm really glad it does. And it's one of those little things that you learn. I don't even remember how I learned that. Like where I got that from. Anyway, continuing. I'm going to completely dismantle this thing today. So soak that and twink. Couldn't be easier. Alright. And last but not least, I need to get this off of here. And there's now rubbing alcohol all over the place. I'm so glad I don't smoke. Let's make sure you can see that. Doink, and it just pops right off. And it's nice and clean. We're done. We are done. that away. Now, just open this up and we'll take one more look at the circuitry inside and we'll see how everything internally is hooked up. One of the things I'm going to have for you is, if you're interested in what's exactly going on with this board here, it's a lot simpler than it looks. So I have some schematics that I drew up. I'll include those. And maybe I'll do a little write-up on how it works, although I thought I explained it okay. I'm missing a screw. There it is. There we go. I thought I explained how it works okay, but maybe I'll do a little write-up just in case. Circuitry, and now we need to get these 4 screws out here. Come on. Come on. I think I tightened these up a little much when I put them back in. So if I was going to improve this, or like, you know, quote unquote complete it, to do a proper finished job, what I'd probably do is there seems to be more than enough space in here. I know for a fact you can fit the 9-volt battery in here. Like, it'll go just like that. Although you might want to be careful about the clearance there. If I was going to do that, I would probably perhaps move this electrolytic capacitor here. This is a smoothing cap for the power supply. I might move that off the board and like tuck it down into the gap. No, there's plenty of space up in here. I'd put it up in there. But you can put that battery in and close this up. No problem. There's plenty of space in there. So that's one thing you could do. You could also maybe make, if you move this buzzer, which you can just remove this completely because it doesn't really do anything. I mean, it beeps when you press a button, but you don't necessarily need that. But you can make a new circuit board with your own microcontroller and, you know, maybe an SD card slot or USB connection. You probably want to add some isolation circuits onto that. And you can put your own circuit board in here. I mean, there's plenty of room, especially if you get this out of the way. And of course, you need the crystal. So, and if you put your own microcontroller in here, I don't think, in my opinion, the voltage regulator that this circuit uses has enough guts to this guy right here. I don't think this guy has enough guts to really power anything other than its own chip. So in here we have, while we are here, we'll take a look at these chips here. But I guess maybe we'll first, these are the 20 lines here, plus 2 for the ad hoc power supply. You can see I just tie the battery in right across that capacitor. So that's really just dead simple. As long as this voltage regulator, which is a 5-volt output voltage regulator, as long as you have more than 5 volts in front of it, actually, I think that one might be a 3.3 volts. I'll have to look that up. I wonder if there's a marking, or that's just a transistor. That's not even a voltage regulator. That's a voltage regulator. These are just transistors. I don't know what they're doing. Huh. I haven't really looked at this board much, so I don't really know what's going on. I know this is an op amp. Pretty sure that's an op amp. Hold on a sec. You have to get my little pocket microscope out for this thing. LM2902. That might be a comparator. I forget what that is. And this, yeah, it's a serial EEPROM. So I believe this guy here contained all the calibration data. So it might be interesting to try and attach my logic analyzer to this guy, and when it starts up, try to sniff the information that the chip reads off of that. That could be interesting. I'm just looking, what's the logistics of that? I'd have to find a good way to tie it in. I might have a soldering iron tip that's fine enough to get in there. Little teeny tiny pins. Okay. But these contacts here were all for the LCD. It's just got that zebra strip right in here. You can see it pretty good right there. that carries the signals from the board up into the actual LCD glass module. And just put some tiny little wires across it, solder them right on. I should probably remove these. And that's it. Really, I mean, once you have the data lines out, try to keep these wires as short as possible because there's a lot of noise. And that makes your life very difficult. Although the comparators do a pretty good job of eliminating that noise without adding a lot of load. You don't want to add any load to this either. The capacitance ruins it if you have a lot of capacitance or if you have a lot of load that sucks the current away. Because these elements here are basically capacitive elements. The LCD display, basically little capacitors for each element. And if you have too much extra circuitry attached to it, it can ruin that too, especially with the high refresh rates. And that's about it. Alrighty, I got my soldering iron out and should be up to temperature. Let's check that. Yeah, it sizzles nicely. Okay, great. And I'm just going to try to undo some of the damage I've done here. I guess I'll start with detaching the power lines here. You know what, a pair of tweezers would probably help too. Hold on a second. Not that these wires are particularly dainty, but just something other than my fingertips to get in there and grab this stuff. Let's see, we'll start with you. Doink. And you. Doink. Okay. Nice and easy, we're just taking wires off, and then these are taped across the back here, so we'll just doink, take that tape out, not a problem. Now we just need to remove these. I can probably do these by hand. I'm expecting these to almost pop off. Yep. A little bit of spring load on them. Doink. And come here, you. Not quite as fidgety as putting them back on, I gotta tell you. It's a lot more difficult to get these things on in the first place. These are also very cheap tweezers. Why are you not? Okay. It's because I grabbed more than one wire and it wasn't pulling away. You know what? I'm not even going to use the tweezers anymore. Screw you. Boink, 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 boink. Pluck. Okay, we're halfway done. I should probably invest in new solder tips. This is way too hot, too. I am not a professional solderer by any means, so I don't know a lot about what I'm doing. But I do know that when the tip starts to get red from oxidation, that's probably a bad sign. And there we go. Free at last. I get this to sit flat. Kinda. And that's pretty horrible. So I'm going to try to solder wick that. See how poorly this goes. Probably because I can't really put any pressure on it because that it's not a very flat board. Need some way to hold that. I don't have any kind of fixturing jig or anything. Let's use tape. I use tape for everything. Tape solves all problems. Now, if you could just stay there, that'll be good enough, I think. Got some solder wick and some really crappy flux. I'm going to try to clean up these pads a little bit. That's not too bad. It's not too bad at all. How'd that work out? Hey, it's almost like I know what I'm doing. Nice and smooth. Fantastic. Okay, we're done with the soldering iron. We'll unplug that. Give it a wipe. Yeah, that was way too hot. Way too hot. That's fine. Let's clean the flux off of that. And should be good to go. Those pins were gold before, but now they're tinned in solder. Good old 60-40 lead solder. Ta-da! And we got rubbing alcohol everywhere. Let's start a fire. No, let's not actually do that. That would be a terrible, terrible idea. Right, we're done with this too. Just need a little blotter. Piece of scrap graph paper. It's all good. All right, that's cleaned up. Now I did look up a data sheet for this chip, so it's very tempting to try and hook up a wire lead to it. Do I want to do that? Do I want to do that? If I did that, what lines would I need to tap? Let's see. Serial clock and serial data. So if that green dot just happens to be where pin 1 is. So serial clock is this pin here, and serial data is this pin right next to it. It is really tempting to try and solder wires onto that. I think I might just go for it. I'm just going to use the wires from this thing here and just chop chop. Let's see, these are already tinned on the ends because they were just connected. So I can probably use these. That one's tinned on the end too. Not on the other end because I just cut them. I'm going to try. And this is the kind of stuff you need like a microscope for. I mean, we're getting into surgery levels of small here. So I need to solder onto these 2 pins here. Probably going to regret doing that, but that's okay. Alright, we'll go with that. Is our soldering iron up to temperature? Yes, it is. Yes, it is. Got a little bit of crap flux on there. Maybe straighten these wires out a bit. That is not on there yet. Now it is. Whew. That was pretty stressful. Not gonna lie. This is some of the finest solder work I've ever done. And I gotta tell you, I cannot see what the hell I'm doing because I can't lean over. And I'm looking at it on a screen, but that does not give me any good depth perception. Nope, not quite. That's not a good smell. Let me re-tin this wire a little bit. A little more solder on it. A little more flux. Flux is good. And now, gotta get right in there. I feel like I almost had it that time. Ooh, I think we got it. I think we got it. Let's have a look-see. Excuse me. I don't see a solder bridge. Hooray! So I got my handy pigtail, which is super duper handy. Plug that into the light bar. Everything's safe, and contact. No smoke. It's working fine. Great. So now the next step is to hook up my logic analyzer and see what, if anything, comes across those pins. Alright, back again. What I've done, I put the battery back on because I don't want to risk blowing up my logic analyzer. It's not the most expensive logic analyzer in the world, but you know what? Better safe than sorry, right? So let's see. We got green status light. That's good. I've also hooked up here. The battery also goes to the terminals in the back here. Because remember, this thing won't turn on unless it sees at least 1.5 volts. So I'm going to hit the switch. It initializes. Good. We're good there. I'm going to turn it back off. And now, let's see. Is everything hooked up right? No, I'm missing... Let's get everything hunky-dory here. I'm going to go from ground here. I just need a ground reference for this guy. I knew I was forgetting something. I always forget something. Which is how things get blown up. Just going to hook this guy into here. Yoink. Okay, now everything is hooked up, I think. So we got here, I have my software set up. This is Pulse View. It's a free software that just happens to work with this logic analyzer, and free is a great price. 2 million samples at 100 kilohertz. I think 100 kilohertz should be enough. And this should give me a good 20 seconds worth of recording. So I'm going to hit run there, and then we'll turn this on. Okay. Turn it off again. Turn it back on. Turn it off again. Turn it back on. We're just trying to get some data here. So if I figure if I give it a couple of cycles, oh, I think it's done. Maybe. Do we get anything? We did. Oh, look at that. There's all our data right there. Isn't that beautiful? Isn't that beautiful? So how many times did I turn it on? I think 3. So 1, 2. This is probably just a hiccup when I turned it off. Probably a hiccup when I turned it off. There's our data. So line 1 is going to be our clock. So clock, data, data. Yeah. And these all, let's see, this is going to be one turn on sequence. So we can have fun. I'm going to try to decode that and see what we get. I have to look up the data sheet, but I think it should be pretty clear. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I don't really know. That's some really bizarre clock signal, isn't it? I wonder if they're all the same. I'll have to superimpose them and see what's going on here. It could also be a... Let's save this, because I don't want to lose it. Save. Bleh. Alright, let's try running this again. Only this time I'll do it at, let's say, 1 megahertz. Or 500 kilohertz. Because I don't need that much time. Run. On. Lurk. Just in time. There's our data. And nope, sure enough. Sure enough. Alright, well, let's check out the data sheet. Maybe, I don't know what's causing this irregular clock signal. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Interesting. But that pattern does not hold up here, so maybe it's just a coincidence. Okay, well, that's interesting. I'm definitely going to save this information, and we'll digest it.